Hi, my name is Harshit Mittal and this is my application called ResearchHub. ResearchHub is a one-stop solution for any research enthusiast. To design this application, I have used both data as a service and model as a service approaches. So we all have come across situations wherein we want to search about some latest technological advancement or maybe look up to an old history book. In order to do so, we end up browsing 50 odd web pages, wasting our time just to land up on a PDF document which is not relevant enough. ResearchHub is a solution to this problem. This is an intelligent ETL application wherein I have consolidated all such academic documents all in one place, such as research papers, journals, articles, book PDFs, etc. The reason why I call it an intelligent tool is because I have provided some convenience features to the users such as summarization, translation, recommending similar documents, and querying the document itself. This is an entire full stack web application which is utilizing FastAPI for the backend design and Streamlit for the front end interface. Let's have a look on the FastAPI Swagger docs. So these are all the endpoints of this application. As you can see, I have logged some crucial endpoints using OAuth JWT authentication technique to make the application more robust and secure. I have built end-to-end data pipeline to extract and pre-process the document's metadata from Springer Nature, which is a publisher, using their public API. So now let's dive into the demo right away. So this is the application homepage and these are the different pages which are logged as of now. We'll need to sign up to access the application. So let's create a user. I have also implemented API rate limiting to make the application more robust against DDoS and similar web attacks. We have three packages, free, gold and platinum, in which the user can make 10, 15 and 20 API calls per hour respectively. Let's move ahead with free and I will sign up. So the user has been created. Let's try to log in with this user. Yeah, we are logged in now. Let's navigate to the main page. So we are giving two functionalities to the user. They can either search by the title of the document directly or they can search by various filters. Let's try this search by title tab first. We have three type of documents in our database: conference papers, articles and books. The user can sort by the date also, and we have implemented partial search as well, so even if the user doesn't know the complete name of the document, they will still get the most relevant documents. So I'll search with the computer, I'll sort by latest. So these are the documents which are present in our database which have computer word in their name. I'll select any document and I'll download it. So basically what's happening here is this document is being fetched from the Springer Nature's website and it is transferred to our own AWS S3 bucket, and the download link from that AWS bucket is being provided to the user. So the user can click on this link and the document will get downloaded in their local directory. This is the document. Let's have a look at the S3 bucket real quick. So this is our S3 bucket which contains the data of our application. This is the database file which contains the metadata of the documents and the user's data, etc. And the documents folder will contain the documents which are downloaded by the user. So these are all the documents which the users have requested to download till now, and this directory will be cleaned automatically every day by an automated process which we'll see later on. And these are the four model as a service features which I talked about. We'll have a look at them in just a moment. So now let's talk about the search by filters tab. So we have different filters which the user can search from. They can search from the subject which they are interested in. They can filter about with the language. They can sort by date. They can directly search by the author or search by the crucial keywords which they are interested in. So let's try to search an article, computer science. I'll sort by latest. Let's leave these filters as of now. So these are the documents which fit into this category. Let's select any document. Sampling. Yeah, so the user can download this document similarly as they did in the search by title feature. And now let's have a look on the model as a service features. So first we'll try to summarize this document. So basically what's happening here is we are using a large language model, which is OpenAI's DaVinci model in this case, to summarize the document. But there is a limitation with any large language model, which is we cannot feed in the entire document at one go for summarization, because there is a tokenization foundation with the model. So we are using LangChain framework to break down the document into smaller chunks. Then each chunk is being sent to the LLM to create a summary of that chunk. So, and then we are summarizing all those chunks together. So basically a summary of a chunk is getting created and stored, and then a summary of all those summaries is created using the LLM. So this is the summary of the document which we selected. The user can read through it, and they can decide whether they want to download the entire document or not. And also in case of large documents, we are only scraping the first 25,000 characters of the document, which is because it is not feasible to feed the entire document for summary generation. We are just reading the first 25,000 characters, which is approximately 15 pages. And the reason behind this is the first 15 pages contain the most crucial information, such as the table of contents, introduction, abstract, etc. And this information is sufficient enough to generate the summary. So now let's talk about the translation feature. So we are using the Google API, Google Translate API for translation, and these are the multiple languages which the user can select to translate the document into. And I cannot demonstrate the translate feature right now because the API is a paid one and I have exhausted it already. But this is the result when I tested it. So this was the original document, and we are not just translating it into plain text. We are even retaining the font size and font family of the original document and reproducing a translated PDF to give a more enhanced experience to the user. Let's talk about the recommendation feature next. So we have built a recommendation engine using semantic similarity based recommendation. For this purpose, we are first converting all the documents which are present in our database into text embeddings. To convert the document into embeddings, we are using a sentence transformer model, and then we are storing those embeddings into a vector database, which is Pinecone in our case. Then when a user selects any document of their choice, we are comparing the embeddings of this document to the embeddings of all the documents from our database and then returning the most similar documents based on their semantic similarities. And also we will also showcase the match percentage of each document to the document which the user selected. So these are the 5 documents and their percentage match respectively. This is the Pinecone index which is being used for the recommendation functionality, and it is of 384 dimensions because the embeddings are of 384 dimensions, and these are the total vectors. Now let's have a look at the last but certainly the most fascinating feature of this application, which is smart docs. So now once the user has shortlisted and selected the document which they want to read, it's still a daunting task to skim through a 600-page PDF document. If the user is interested in studying only about one particular topic, it's very trivial to go through the entire document. So the user might then do a simple keyword search through their entire document, but that is not an efficient way to search the document. Reason being, the keyword might be used in multiple places and in different contexts from what the user might want. So we have implemented semantic similarity based search in for querying the document. So let's try to query this document. First, under the hood, what's happening is, first we are encoding this document into text embeddings, but the entire document is not converted at one go. We are breaking the document into smaller chunks of 2000 characters each, and then converting each chunk into a text embedding using the sentence transformer model. Then the user can ask their query, and this query will also get converted into similar encodings using the same model, and all these embeddings will be stored in the vector database, which is Pinecone. Then we'll perform a similarity search on the embeddings of the query and the embeddings of the various chunks of the document, and the chunk which is most similar to the query embeddings will be extracted. Then this chunk will be passed as a context to our large language model, which is OpenAI's GPT 3.5 in this case. So this is demonstrated here through this code. This is the sentence transformer model which we are using to generate vector embeddings of our text documents. So we are loading the PDF document and we are breaking it down into smaller chunks of 2000 characters each. Then we are generating the embeddings for each individual chunk and pushing it to our vector database, which is Pinecone. So when the user asks any queries, we will encode that query using the same sentence transformer model and push it to our vector database. Then we will do a similarity search between the embeddings of our query and all the embeddings of different chunks from the document, and the chunk which is most similar to the query, that will be retrieved and passed as a context to our large language model, which is GPT 3.5, and GPT 3.5 will then generate an output based on the query and the provided context. This document is encoded. Now let's ask some query. What is sampling? So we have received an answer based on the information from the document. Sampling is a method used for sparsifying the graph multiple times, etc. And the beauty of this implementation is, if we ask any irrelevant question which the information for which is not present in the document, the LLM will not hallucinate and will not use its own intelligence to answer that question. It will simply say that the information is not present. So let's try with any relevant question. What is the weather today? Yeah, so we got the output as information not available in the document. So that's the complete demo of the application. We have also implemented dashboarding. The user can check what all actions they performed, how many calls they made last 24 hours full time, and they can judge their usage. So that's about it with the demo. And this is the vector database which we are using for the smart doc functionality. Yeah, so this is the GitHub repository. You can refer to it for the complete code. This is the architecture diagram of the application. So the user interacts with the Streamlit front-end application, which talks to the FastAPI backend design. Both these applications are Dockerized, and the Docker image are hosted on the Docker Hub platform. These are the Docker images. And then we are also using Airflow DAGs to automate certain processes. One such process is scraping the metadata, storing the metadata in SQLite database, performing some data quality checks using Great Expectations, and storing the database file in our S3 bucket. And we are also encoding all the documents into our vector database, which we talked about in for the recommendation functionality. This process is also automated through an Airflow DAG because this is a time-taking process. Let's have a look at the Airflow DAG. So this is the DAG which we were talking about. It performs three functionalities: scraping the metadata, storing the metadata in a database file and pushing to our S3 bucket, and vector encoding of all the documents into our Pinecone database, which will be used later on for recommendation. We also have one more DAG which is used to cleanse our S3 bucket on a daily basis, and it will remove the older documents which the user downloaded from our application. Let's check the DAG also. So this is the delete files DAG, which is responsible for cleaning our S3 bucket. And we are using Great Expectations to perform some data cleaning, data validation checks. This is the report for that. We have 11 test cases and all of them are successfully passed. And we are logging all the user actions in our AWS CloudWatch logs. And these are the 4 model as a service functionalities which we just saw. We have also implemented GitHub continuous integration, which is automatically used to test any code changes which we are performing in our code base every time when we push any changes to the GitHub repository. This will streamline the development process and save time for testing. And this is the technical documentation which covers the entire flow and the journey, how the application was built, and all the code snippets are also provided. Please refer to this documentation in case of further queries. And this entire application is hosted on a GCP VM compute instance to make this application available publicly. So that's about it. Please refer to this GitHub repository to check out the complete code. Thanks a lot.